Welcome back to Programming with Adam, and in this video we will be looking at LeetCode questions. The next one is balanced binary tree, and my solution for this looks like that. So it looks pretty compact. I have tried to make it not look very long because I want to like explain one line at a time. So that will basically shorten the exposition. So what I have actually done here is first define a method not balance or depth. So basically it takes a tree as it at a root input. So it basically takes a tree and it spits out an integer. So either it's -1, which corresponds to it's not balanced, or if it is balanced, then it will just spit out the depth of that tree. So let's see. If the tree we put in is empty, then it is balanced and its depth is 0. So we are returning 0. Then we are looking at, okay, if what is the left depth? Okay, so then we are applying recursively this method to the left child of the root. Okay, and then if we get a -1, then that means that that subtree is not balanced. Okay, to have a balanced tree, you need that the subtrees are balanced as well. And so if the subtree root left is not balanced, then of course we have to return -1. Similarly, if we are looking for the right tree and checking is it if it so checking if it is balanced, and if the result at and if its depth is -1, that means it's not balanced and we have to return -1. Now let's stop for a second here. At this point, we know that both left and right trees are balanced. Okay, cool. So so what is left to check? Well, we need to compare. Let's say one of them was has. So now notice, because they're both balanced, right depth and left depth, it's simply spitting out what is their actual depth. So the problem is if there's too big of a difference in their depth. So if the absolute value of the difference is greater than 1, we have a problem. It's not balanced. And then we have to return -1. In all other cases, we know that root is, so if the absolute value is 1 or less, and we know, remember, we know that the subtrees are balanced, and we know at the difference now at this point, if we get to the else, that in the else root is, so we know when we get past this if and we are not returning -1, then what do we know? We know that the subtrees are balanced, and we know the difference of the depth is 1 or 0. So that means that root is balanced. So if it is balanced, then what do? Well, we simply have to return its depth. So that will be taking the depth of the left, depth of the right, take the maximum of those, and then adding 1. Okay, so that's the procedure. So either it returns -1 if it's not balanced, or it actually spits out the depth. And then the is balanced, we simply figure out whether it is if it's -1 or not. If it is -1, if the result of this thing here, if we call the root and the result is -1, that means it's not balanced. if the result is -1. So therefore, we're comparing if it is, yeah, maybe that's a little bit confusing here. I don't know. If the result of this spits out -1, right? So that means that the subtrees, or there was some other problem, basically we need to return a false, right? Because there is some sort of problem. And then how do we return a false? Well, we are just comparing the -1. Is it different from -1? And that will return a false. Alternatively, if everything goes perfectly and the tree is actually balanced, then what will this return? It will return the depth. So that will be some number. And so it's perfectly balanced. And this returns the depth. Well, so of course, the depth is different from -1, and it will give you a true. So yes, it is balanced, and we are done. So that is, this is perhaps not so reading friendly, but it does work in the end. Okay. So let's now look at the performance time. As you can see, this is 99.72%. So this is super fast, and I don't think you can do much better than this. So that's it for this video, and I will stop here.